let's get started. So first, a little bit about me. I'm currently based in San Diego, California. Lived here for about 3 years. Prior to that, I lived in Columbus, Ohio for a handful of years. Live here with my family. Interests are including video games, basketball, American football, golf. I am not good at any of them, but I have a good time, and that's all that matters. My background, kind of career and educationally, I've hopped around a little bit. My training's in kind of sociology, statistics there. Kind of my focus there was on education and measuring educational attainment, fun stuff like that. Got my start career-wise in analytics in kind of a retail customer analytics environment. So looking a lot into like segmentation and churn and targeting and things like that. Moved a little bit into advertising for a while. We're working on experimentation experimentation, attribution, and working on bidding machines to bid for ad space and try to optimize that using machine learning. Had a little foray into kind of general data science consulting, doing some with, everything from pharmaceutical companies to modeling construction project overages and stuff like that. And then for the past couple of years, I have been in financial services at LPL Financial. I'm a VP of data science there right now. If you're not familiar with LPL, we're one of America's largest independent broker dealers. We have about 21,000 advisors with a little over $1 trillion in AUM. So given that our advisors are independent, our job is to support them as they kind of own their own businesses and manage their own clients, to kind of help them run the most successful small businesses possible. So I'm going to start off with what I'm calling a term I'm calling event modeling, which is can be reclassified as kind of classification plus time. I'm going to go into that and then show how classification works there, and then kind of go into survival analysis and how that can potentially be a better approach. So a question I often get as data scientist, this has been true kind of throughout my career and in any stop really, is will X happen? Will something, a business process, happen sometime in the future? And so in a retail example, that question is, will this customer make another purchase? And given that information, we can know how to market to them, how rich to give an offer, stuff like that. In advertising is, will a viewer click on this ad? That affects how much you want to bid on the ad space. You don't want to bid on stuff that someone's not going to interact with. Getting into financials, like, will this advisor cross a certain AUM threshold? Are they going to grow to a specific threshold? We have different tiers within our business, and so we can know if an advisor is an advisor going to reach that, and then kind of qualify for that next tier of service. As an independent broker dealer, we do have kind of an offering of services for our advisors. That can be stuff like bookkeeping, an outsourced CFO, marketing solutions, and things like that. They're very interested in, is an advisor going to purchase one of these in the near future, or do they look like someone who's going to purchase them? And then where I'm kind of neck deep right now is around churn with advisors and with our end investors. So are they going to leave? That's an important question. Do we have a healthy advisor base? Do each of those advisors have a healthy client base? How much turnover can we expect in the next however long? Hopefully for people working in industry and in academia too, these kind of questions resonate as similar ones that you get asked or problems you are tasked to solve. Focusing a little further in on financial services, I'm going to talk a lot about churn today, but churn can apply to lots of different areas. It can be a product. How long is an advisor going to be invested in a business product, an investment product? kind of what's their tenure, for how long are they going to be into that. It can be a client. How long are they going to be staying with their advisor? Are they going to take their money and move elsewhere? An internal advisor, we obviously want to keep as many advisors as we can. So looking at the risk of that turnover. For external advisors, ones who don't work, we want to see, ideally, if we want to recruit them to come to LPL, we want to go after the ones we think are probably likely to make a move in the next little while. And then also our home office employees. We see, HR can see who's at risk, who's not, and kind of determine interactions that way. This can go to product usage too. Like if someone's already using a product, what's the likelihood of them stopping using that? Or on the other hand, if they're not using a product, what's the likelihood of them starting to use it? And so the sales folks can kind of focus their efforts there. And then with all these kind of sales pipelines, a lot of them can be kind of reduced to funnels or series of events. What's the likelihood of this opportunity reaching stage 1, stage 2, stage 3? How far do we expect them to get through, to kind of find inefficiencies there, potential bottlenecks, and to make that process as smooth as possible. And then also compliance events too. Do we think there's a likelihood or a risk of a firm violating a rule of some kind? So we can proactively do interventions, check in with them, make sure stuff is all in order, and then also see, factors that might predict those as well. So this kind of question of will something happen is pretty ubiquitous throughout the data science space broadly, and in financial services as well. And one point I want to make too is when you see these questions, I think our brains initially go straight to classification. We can use a logistic regression or an XGBoost or any kind of classification algorithm. Let's just say, yes, this is going to happen. No, it's not going to happen. Get our variables together, get our features engineered, and then make a prediction. What the complication of that is there's always, in these cases, a time component. I'll argue that time is completely inextricable from these cases. You can't model these unless you're taking time into account. Sticking with churn, if you ask the question, will someone churn? The answer is 100% of the time, yes, they will, eventually. I don't think anyone, it's pretty rare for someone to stay with a single firm for their entire career. Not to get too morbid, but we are talking about survival analysis here. Eventually everyone's going to pass away as well. So if we look a few decades into the future, your customer base might be completely churned over. Your advisor base might be completely turned over. Every single advisor you have, every single employee you have is eventually going to leave. So we could say, if we wanted to give 100% accurate classification, we can say, yes, everybody is going to turn. That's obviously not very useful. And even in cases where the answer isn't 100%, because obviously not 100% of people are going to buy every product that there is, the timing matters. Every business initiative is time boxed in some way, whether you're looking at a month ahead, a week ahead, next quarter, next year. There's always a time box for when this matters. And so the point to take away here is time is a completely necessary component in looking at whether or not an event is going to happen. It kind of shifts the question to, is this event going to happen, to either is this event going to happen within a time box, or when is this event going to happen? Kind of the simple classification approach you can use is kind of just set a time limit there. So going back to churn, which we'll talk about a lot here, we can say, did this client churn within 6 months of a certain time period? And we can ping them as 1 if the answer is yes, and ping them as 0 if the answer is no. And then apply your traditional ML statistical approach, how you would answer any kind of classification problem. Here's kind of an example of that, and I'll admit this is kind of like edge case a little bit to illustrate a point. But let's just say we look at 4 clients, and there's a 12-month study period. So client A churned in month 1, and so under this 6-month label period, it's a 6-month churn period that we're using as our label, they would be classified as, yes, a churn. Client B churned 5 months after the period started, and they would be labeled a churn as well. Client C churned 7 months after the period, but they would not be labeled a churn because they didn't churn within 6 months. And client D made it through the entire period without churning, and they would not be labeled a churn as well. And so the question you have to ask is, for each of these cases, is it proper for them to be grouped together? And that really depends on your question. Do we want to treat someone who churned 1 month the same as someone who churned in 5 months? Also, we see that these two are more similar in the months to churn than A and B are. Do we want to separate these people? Is that arbitrary time box appropriate? And then also too, do we want to treat people who client C and client D the same, someone who did churn versus someone who didn't churn? It's again entirely possible for those to be justified inferences. Every time we do a model, we're doing an abstraction of some kind, so it could be justified, but you do have to take it into consideration. Like, are A and B more similar than B and C? Is it proper to separate them and put them apart? That kind of stuff. And then you also have to think about what you do with people who haven't churned at all. Another criticism as well is if you have a 6-month period to see if someone's going to churn or not, you can't retrain on data that's newer than 6 months, or else that would bias your data set. So you have to have every single observation has the same opportunity to churn. They need that entire 6-month period, or else your newer cases will be biased towards not churning because they don't have the proper, they don't have the necessary time for that to happen. And that could be, I mean, that could be fine, or that could be a big deal, because if you anticipate something or you see something that happens within a 6-month time period or within your time box period, your model won't be able to pick that up for that equal time period. So those are some of the kind of shortcomings that I see with using a classification approach for those kinds of will X happen questions. And so now let's look at survival analysis and how this potentially offsets those. So to give kind of a basic background in survival analysis, it's kind of founded in medical research, as the name implies. You're modeling actual survival and mortality. An example would be, how does a treatment affect mortality in tuberculosis patients? And what they're really looking for in that question, because again, all of us eventually pass away, they want to look at how this treatment affects the time it takes for that event to occur. We have to have a timely study. We can't just wait till every single sample member of the study passes away. That could be decades from now. Check-in times are likely to be irregular, especially if this is kind of an audit study with medical, like looking at a doctor's office visits and things like that. But the question kind of shifts to how, rather than do people who take this medication pass away at a lower rate, it's kind of looking at how long it takes how this medication affects how long it takes for that event to occur. And in our case, survival equals client tenure. But this could also equal lots of things like how long it takes for them to buy a product. Going back to our use cases, the survival is whatever you define it to be. Just a fun little bit of I guess, like, morbid language there, and just how the naming is set up. So some of the strengths of survival analysis are we're using time to conversion as the dependent variable. Rather than just using a yes/no and grouping everyone together, we're using how long it takes for that event to occur as the dependent variable. And we can use incomplete observations here. So we don't have to have that kind of waiting period to analyze a case. As the new cases come in, the information helps update the model, even if it's within 1 month. Knowing that someone survived 1 month or didn't survive 1 month is useful information for the model. And it asks a more detailed question, which allows you to get more detailed answers out. And And as Drake here shows, it shifts the question from will this client churn to when will this client churn? And kind of going back to our example, that is right here. Rather than just looking at this yes, no label, we're using all of this information in this months label. We know how far they get. We treat all these cases differently. And we can, we use this kind of censorship label where we know client D is eventually going to churn, but we know after 12 months they haven't. And we can use the timeline here and the fact that all of these clients have churned. So it treats them in a more continuous manner rather than grouping them into these two cases here. So in survival analysis, as basic survival analysis, there's a few different families that you can go down. So this isn't a full survey of every survival analysis approach. But in kind of at the most basic level, there's two main functions that you can use. One is that you use. One is the survival function. And that's basically answering the question, like kind of building a decay curve or a survival curve. How likely is someone to survive past time X? So like how likely are they to survive past 3 months, 12 months, 24 months, however long you have for your study. And then there's a hazard function, which tells us how much more or less likely is this particular case to have the event occur than an average case. And I'm going to go into more detail on both of these now, but these are just kind of the two components of how I do survival analysis in these cases. So first is the survival function. And this kind of, you set one curve for the whole data set for the most part. And you can look at after 2 months, what % of cases remain. After 12 months, what % of cases remain. You also can break this apart by groups. I'll show some examples of that. It's a useful EDA tool, but oftentimes we want to get more detailed, more granular, and see how individual factors affect performance there. So here's kind of an example of a single survival curve. We see this here where there's just kind of this decay function right here, and we can look at days and then overall survival probability. So days on the x-axis, overall survival probability on the y-axis. And we go here and it says, you know, after 250 days, an average person is 60 something % likely to survive. After 500 days, it's closer to 25% and so on. You can kind of see you have like a baseline expectation of how long you would expect someone to go to survive, or in our case, to not churn. So this is good for kind of aggregate statistics. Looking at an advisor's client base or something, you can kind of see what the expected churn rate is going to be. Spoiler alert, without getting into too much proprietary detail, this all stays very close to 100% for a very long time, unless something is severely wrong. And then here's an example in American football, where we can kind of see some different approaches. This is Pro Football Focus. This came from them. And they actually use survival analysis to look at how long it takes for a quarterback to get pressured. This is as a way to measure or rate offensive lines. And so here they have, this is in 2019. They have, they compared a couple different curves for different groups. Right here is the NFL average. And so you see here, like for the NFL average, after 3 seconds after snap, there's only a 40% chance that the quarterback hasn't been pressured by that point on a given snap. But they look at the Green Bay Packers for this slide as well. And you see for them, after 3 seconds after snap, there's about a 50% chance that the quarterback hasn't been sacked yet or hasn't been pressured yet. And so that would imply here that the Packers offensive line is better than the NFL average because they're able to give their quarterback more time to throw without having a defender close to him. So you can kind of see here how you could look at different groups. And this could be different advisors. This could be advisors of different affiliation models, things like that. you can kind of see how different ways would go to break these apart. There's lots of examples there if you look for Kaplan-Meier curves. That's kind of this process here, and it'll show different ways to break this down. But the overall thing I want to take away is this kind of sets a baseline expectation at a given time point for how likely it is someone is to have had the event occur. And so the next component of this is what's called the hazard function. And this is a statistical / machine learning model that outputs what's called a hazard ratio. And what is a hazard ratio? Kind of the interpretation here is like if you get a 1 in a hazard ratio, this case is no different than the baseline hazard. It is as likely as the baseline hazard to have the event occur. So if I'm looking at 3 seconds, a 1 would be, they would have around a 40%. 2.5 would be something like this case has an expected hazard 2.5 times higher than the baseline. And a 0.5 would be this case has an expected hazard of half of that of the baseline. So you can kind of see how it shifts up and down, where you can kind of see the general interpretation there of how what the output of this kind of model is, and how it can be interpreted. This is what is called a semi-parametric model, where these specific kind of Cox models here, these hazard models, don't make any assumptions regarding the underlying survival curve, but assumes that there is one, that there is a decay curve present, but it's not making any assumptions regarding what exactly that looks like. That could take any shape, could have any form. It's not explicitly saying they have a 90% chance at this point or a 10% chance at this point. It's just saying it's higher or lower than the average. And then next, kind of to go a little bit under the hood, the kind of hello world and most common way to fit these hazards is using a Cox proportional hazard model. And at a high level, it's pretty analogous to linear logistic regression and how it works. Basically, every case gets a coefficient. Those coefficients are aggregated. Then you get out the hazard ratio rather than a point estimate or an odds estimate. Here's the formula here. I am not great with web text. I couldn't get this shrunken down because I'm using a different kind of presentation software. So sorry for the granularness. But you see here your kind of common like weights, inputs. You aggregate those up, exponentiate them, and then that puts out your hazard ratio there. It's nice and similar to linear logistic regression that it's interpretable. Every variable gets a coefficient. You can see how every single prediction gets made. You can analyze those coefficients to see what kind of matters more in the process of this event occurring or not. And that's kind of how that one goes there. This is pretty small. You probably can't see it, but there's I have the link in the presentation as well. This is an example of using survival analysis for marketing attribution, which is a pretty interesting approach. And as you can kind of see really small on here, here they plot out the coefficients for each of a variety of inputs and predicting if a purchase is going to occur. And so you can kind of see what kind of, they're talking about like mobile phone types and all this kind of stuff. You can kind of get a visualization into what matters for how those hazard ratios are generated. Now there's one key assumption here. I mentioned it before, proportional hazards. What the proportional hazards assumption is that if I say someone's 2.5 times more likely for an event to occur, that means they're 2.5 times more likely across the entire decay spectrum. They're 2.5 times more likely at 1 month. They're 2.5 times more likely at 3 months. They're 2.5 more times more likely at 12 months, which is a pretty strong assumption. This is saying that these hazards this hazard ratio doesn't change over time. There are ways to get around this assumption with some, this sounds like cheating, but creative data engineering. It's really just ways to set up your problem so you can actually explicitly look at how hazards would change over time. It just kind of takes some data engineering and different data structures, but it is possible to get around it. And also, if you look at the Lifelines doc, this Lifelines is a survival analysis package in Python. And they actually have, the authors lay out here some points of when you don't need to worry about the proportional hazards function, which is worth looking into. But it's definitely an assumption you have to work around. And if you are going to ignore it, you need to know why you're ignoring it. But how you enforce this is kind of strictly up to the researcher and what assumptions you're fine violating and what ones you need to keep for your analysis to be valid. I talked about this as kind of a linear logistic regression analog. The Cox models are implemented in other machine learning libraries. XGBoost has an implementation where you have to kind of alter your data structure a little bit, but you just set objective equal to survival Cox, your evaluation metric as to Cox negative log likelihood. And you can use the same infrastructure that we all use with XGBoost, as it's a great tool. And there's a deep learning framework called DeepServe. I have not used it before. I'm aware of its existence, but I haven't been able to actually evaluate it there. But I know it's out there, and I wanted to send it out to the group. There's a few survival libraries in both R and Python. I have in R, there's survival that comes with base R, and then there's censored. That's a newer one that fits survival models into the tidy models framework. With Python, it's Lifelines. There's, from focusing more on Cox models and those hazard stuff, there's a scikit survival, which kind of puts the survival models into the scikit-learn API. And there's also DeepServe as well that exists as a Python package, even though I think it's implemented in Theano. So like Captain Planet here, we can, with our powers combined, with the survival function and a hazard ratio, if those all are, again, properly estimated, which is a big assumption, you'd be able to estimate the probability of an event occurring at any time for any individual observation. So if you have that baseline hazard and a hazard ratio, you could say client A is X% likely to churn at month 1, they're X% likely to churn at month 5, and so on down the list. That gives you a tremendous amount of flexibility for how stakeholders and business users could approach questions. You could have one model that potentially goes to different use cases, where one team is focused on this upcoming quarter, the next one is focused on this year. How each hazard ratio differs. You could look at different interventions. Like for this approach right here, let's just hopefully say our model is properly calibrated. Client A would ideally have a higher hazard ratio than client B. These two people's hazard ratios would be pretty similar, and then this one would be a lot lower. So how we would be treating these cases is, if properly estimated, client A would have the highest hazard ratio. These two would kind of be in the middle here, and client D would have the lowest. So you have kind of 3 tiers of how you want to treat these people, rather than bifurcating on a given line. So kind of when to choose each approach. This is just kind of according to my experience. I don't have a fully, I guess, like systematic way to evaluate that. But kind of from my experience, when to choose classification is if there's a clear time period where 6 months really matters, and that's the clear business problem. Just use XGBoost to predict the 6-month scenario, or a linear logistic regression. If you need a quick model for a POC, just to get something up and running, the infrastructure for classification models is much more robust than that for survival models, so you can get moving a lot quicker. And and you have reason not to expect dramatic short-term changes. So again, like we talked about, if you have a 6-month time period, you can't evaluate new cases until they've been in the process for 6 months. If you don't expect anything major, or you haven't seen anything major in that time period, it's safer to use a classification model. And just kind of practically speaking, if you need to integrate with a platform, you're probably going to be a lot better off with a classification model. I'm thinking like a data robot, or another AutoML platform of that kind, where they kind of have out of the box support for classification algorithms, but a lot of times they won't for survival. And even if they have a way to like bring your own model, like in SageMaker, you are going to have to do some integration work to make that work. So if that's not a possibility for you to do, and a classification model probably works a little bit better. When to choose survival is, again, I think it's a more detailed and more, it's more asking the real business question. If you have more time to devote to development, because again, you're fitting 2 functions, you're estimating 2 functions instead of 1. That introduces, twice as much complication for what could go wrong, how to estimate stuff. You're using a less familiar data structure. I won't even say more difficult, because sometimes the survival data structures can be easier, because you can just kind of take event logs, add some lead and lag variables to them, and you're good to go. But it is less familiar for people who've come up really just honing in on regression and classification. You have more time to integrate to integration. I'm thinking of kind of the SageMaker bring your own model component there, where you can take a model, and specify to SageMaker what you want the inputs and outputs to be, what they're going to look like. You can write the loss functions and things like that. If you have time to do that, I think it's worth doing, but that's not always the case. And if you want this model to be kind of a foundational model that can inform potentially multiple efforts, like we have a churn model for our end investors right now. It's possible that different investors are going to want different time scenarios. A small 1-person investment shop is going to have different needs than an institution that has 100 advisors. And then for prioritization use cases, the survival analysis stands out, because in this case, in prioritization cases, the Cox model can really stand alone, because again, you don't have to fit the underlying survival curve. So it'll just give you a ranked list, if you have this predict function for all your cases, of who's at most risk of churning, who's at least risk of churning. You can kind of just work your way down there. So if your use case is really around prioritization, a survival model can be pretty strong, and a Cox model can kind of stand alone without having to fit a survival curve as well. So, I mean, full transparency, I gave a talk on why survival analysis is super great. For our current churn models, I'm using our classification approach right now. One is it's good enough for what we need right now. We got some pretty good results with what we need, and good enough to kind of get the business invested into it. And so that's, there's always more work to do on a model, but you kind of try to get to good enough and then try to start implementing. We're incorporating this into our AWS platform, and classification has much stronger out of the box integration, specifically with our ML ops folks. They kind of are familiar with the tool set for how to evaluate those, fit them into monitoring and drift tools and things like that. And we also want to bring along, all my team members as well, and they're familiar with classification as well. And so it's kind of a less than ideal model, but it can be implemented, which is a trade-off you have to make. But I do have survival model queued up as a potential enhancement. I've done a POC on it to kind of show the differences and show what else we can answer with it. But it's not fully implemented yet. So just to kind of give a insight into how we're actually doing this, and even though I hopefully didn't come across too hard on a straight up classification approach, it's actually what I'm using at my job today. And so there's always trade-offs and considerations, and kind of what you have to do with that. And that is all I have for today. Thanks everyone for your time, and I'm open to any questions now.